A crash course on functions. Let's start by looking at an informal definition of a function. So a function is like a machine that takes in a value from the domain, and we usually call those values x or t values. It does math stuff to it, and that's why I call this an informal definition. And then it lets out one value in the range, and we usually call that value the y value or the function's value. So here's a little image to go along with what's happening. So we have these values in the domain, usually x values, that go into the function. And then stuff happens to those x values. So what happens to them? Mathematical stuff, mathematical operations. So we can add x values together, or we can subtract, we can multiply them, we can divide them, or we can perform special math operations or special math functions are ones like trig functions. So we can perform the sine function to x, or the tangent function, or logarithmic functions, so log of x. So there's a lot of different things we can do to this input value of x, and what comes out after we perform those operations are values in the range. And we usually indicate those with y values, or the function notation f of x. So this math stuff, you can think of that as the function f is happening to x, so what comes out is f of x. Formally, the domain is all of the input values that give us some output value. So we can plug in some x that will give us something that makes sense as an output. And then the range is all the output values, so all the stuff that comes out once all of the input has gone in. So this is just a very basic definition of a function to really try to understand what's happening as you substitute x values in, why you get out y values. And this is the foundation of calculus. We deal primarily with functions. So let's go ahead and take a look at some specific functions and what we can do with them. So two of the most basic things we can do with a function is we can evaluate it and we can graph it. So let's look at this function, f of x equals x squared plus 1. And we'll start by evaluating it. So this notation, f of 3, means that we want to substitute in this number 3 anywhere there's an x. So you'll notice that the 3 is in the same position as the x in the function notation, f of x. So we're going to substitute in a 3 everywhere else we see an x in the function. So we're going to put that 3 right here and square it and add 1. So f of 3 is going to become 3 squared plus 1. So 3 squared is 9. 9 plus 1 equals 10. So we've evaluated the function f of x at a particular value. So this number 3 is going to fall in the domain of the function because I can substitute in 3 and I got out a number. 10 is a very real number. And this actually corresponds to a coordinate point. So we substituted in an x value and we got out a y value of 10. So this, evaluating this function at 3, gave us a coordinate point 3, 10. So we'll just hold on to that and think about that when we go back to this graphing portion of the problem. The next thing I'm told to evaluate is the function at pi. So a lot of students have a hard time when the number is an irrational number like pi. So pi is a number, and we can go ahead and plug it into the x value just like we did the number 3, because remember pi is 3.14159, etc. So there's nothing wrong with substituting pi into this x just like we did the 3. So f of pi means that we're still going to put a pi everywhere there was an x in the function. So we're going to have pi squared plus 1. Now the only difference is that I'm not going to carry out this operation. So pi squared is not really an operation that I can do by hand because pi is an infinite number. So I could plug this into my calculator, but I really want you to understand that it would actually be better to leave our answer as pi squared plus 1 rather than to substitute pi squared into my calculator and add 1, because what would then come out is ultimately an approximation. So pi squared plus 1 in my calculator, well, that's also going to be an answer that goes on and on forever, so I can't write it all out. So what I'd have to do is I'd have to stop somewhere. So I'd have to round or truncate or cut off the answer, and instead of doing that, I'm just going to leave my answer as pi squared plus 1. That is the exact answer. And it too corresponds to a coordinate point. So it corresponds to the point pi squared plus 1. Now, it's not a very nice coordinate point. It's not going to be a very nice thing to graph because we don't really even know what pi squared plus 1 is without a calculator exactly, but it is a coordinate point, and it does work the same way as substituting in a 3. So finally, the last thing I want to do is substitute in an expression. So say we don't know the exact number we're plugging in, like 3 or pi, but we do want to plug in x plus h, where x and h are variables that stand for some number that we can plug in. So I'm going to follow the same method. Anywhere there was an x in the original function, I'm going to now substitute this entire expression, x plus h, is going to go into each of those x's. So f of x plus h is going to equal the quantity, the expression, x plus h. So what's happening to that x? Well, it's being squared, and then we add 1 to it. So now, this is definitely not worth expanding or distributing. So x plus h squared, a lot of students are going to want to distribute. So x plus h times x plus h plus 1, and then say x times h, etc. That's not really worth it because it doesn't look any nicer. So the only time we'd really want to go through that trouble is when we can make the problem look simpler, and that would in fact make it look a lot more messy. So that's not really worth doing. One little pitfall students are going to have too is that they're going to want to distribute this power, this exponent here, to each of these variables, and that is definitely not true. So just to clarify, this is not the same as x squared plus h squared, right? That distributive type of property does not happen with exponents. We would have to distribute, as in multiply x plus h times x plus h, not just move this exponent to both of those variables. So neither of those, one we can't do, the other one we shouldn't do. We should just leave our answer like this. So f of x plus h is x plus h squared as a quantity plus 1. And we really probably wouldn't write this as a coordinate point because they're not in fact numbers. They are only variables that stand for numbers. So now we've evaluated a function for different function values. So the next thing we want to do is we want to graph this function, x squared plus 1. Now, there is a lot better way to graph this function than what I'm about to do. What I'm about to do is the really rudimentary way of graphing a function, but one that always works for polynomials such as x squared plus 1, which is substitute in x values and get out y values to create a bunch of coordinate points. So we've already done that for one nice pair of coordinate points. I'll go ahead and use a different color. We have one pair of coordinate points. We have 3, 10. So on my xy plane over here, I have 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll go off the grid a little bit. So here we have that coordinate point 3, 10 as part of my graph. So let's go ahead and pick some easier numbers. Let's go ahead and plug in 1. So we're going to evaluate f of 1. So again, we substitute 1 in for this x, so we get 1 squared plus 1. So 1 squared is 1 plus 1 is 2, so my corresponding coordinate point is 1, 2. So I go to the right one and up 2. So there's another coordinate point. And then how about I go ahead and plug in 0. 0 is a nice number to plug in, so f of 0 is going to be 0 squared plus 1, letting 0 replace my x. So 0, 1 is going to be another point on the graph. And how about we go ahead and plug in negative 1. So f of negative 1. So negative 1 into that x is going to give me negative 1 as a quantity squared. So the negative is also being raised to the power of 2 plus 1. So negative 1 squared, well, the negative is going to go away, and I'm going to just get positive 1 plus 1, so I'm going to get out 2. So my corresponding coordinate point is negative 1, 2. This one here, just to be thorough, was 0, 1. So negative 1, 2 is going to be my other point on the graph. And if you did happen to know, x squared plus 1 is a quadratic, so its general shape is a parabola or a U shape, either right side up or upside down. And this one is right side up looking U, so it's not this one. Then we can go ahead and connect the dots, and we can draw a sketch of our parabola to look something like this. Now, that's only if you knew what x squared plus 1, or any quadratic, took the shape of. So it took the shape of a parabola. If you didn't know that, well, what would we have to keep doing? Plugging in points. So we'd have to just keep going. Maybe we would have plugged in -2, -3, -4 until we saw a pattern to be able to connect the dots. I'll tell you right now, this is probably not enough. I only connected the dots because I knew that this original function, x squared plus 1, was a quadratic that had the general shape of a parabola. But I never want you to forget that if necessary, you could graph functions by plotting points, or specific functions like polynomials or rational functions. It gets a little trickier when we get to exponentials, logs, and trig functions. But graphing functions that are polynomials or rationals by plugging in numbers is always a method. Definitely not the most efficient one, but a way to graph any function. Alright, so now we move on to talking about properties of functions. So there are different ways we can describe different aspects of a function, and the first thing we're going to start with is talking about when a function is increasing, decreasing, or constant over an x interval. So first things first, how do you read a function? You read a function from left to right. So from left to right, just like you'd read a book. And we read it along the x-axis. So what we're kind of saying is, what's happening to the y values as I move along from left to right along the x-axis? So here on the x-axis, here's negative infinity way over here, and here's positive infinity way over here on the x-axis. And we think about, well, what happens to the y values as I move from left to right along the x-axis? So my function values, my y values, can be increasing from left to right, they could be decreasing, or they can be staying the same over a particular x interval. So here on this graph, let's go ahead and mark the x-axis. So this would be -1, -2, -3, -4, -5, and then 1, 2, 3, 4, 5, and 6. And then way over here again is negative infinity. So if I wanted to describe this function from -5 to -4, this function here is staying the same. So these y values aren't going higher or going lower, they're staying the same. So on this interval, I would be considered constant. But starting at -4, and as I move along, and I move along, and I move along, all the way up to this x value of 0, so again, I read from left to right, so from -4 all the way to 0, what's happening to these y values? Well, they're getting smaller. So that would mean that this function is considered to be decreasing. So along this portion of the graph, I'm decreasing all the way up to here at 0. And from 0 to 1, you can guess, because we just described another portion of the graph as constant, from 0 to 1, I am a constant function again, because my values are staying the same. And from 1 to 2, so from this x value of 1 to this x value of 2, what's happening to the y values? Well, they're getting bigger, like I'm walking up a hill. So this would be considered increasing. And then finally, from 2, so from this x value of 2 all the way to infinity, because this arrow indicates that this goes down and down and down forever to infinity, then I know that this graph changes to decreasing as my values are getting smaller, right? So the values are decreasing here. So it's nice to go ahead and label your graph like this. You can go ahead and write constant or C here, and then decreasing or DEC, constant again. But really what we want to do is we want to label them somewhere off of the graph to the side. So where is this function constant? And we write our answers as intervals. So this function is constant on x intervals, right, over an x interval from -5 to -4. so smaller to bigger. So -5 to -4, and the symbol we're going to use for and is this little u, and it was constant from an x value of 0 to an x value of 1. So that's where this function was constant. This function was increasing only from an x value of 1 to an x value of 2. And this function was decreasing from -4 all the way to 0. So from -4 to 0. And this function was decreasing from 2 to infinity. So how did I choose open parentheses? Well, by default, that's the notation we're going to use in this class, is that when we're describing intervals, we're going to use open parentheses for increasing, decreasing, and constant, because it really doesn't make sense to be increasing at a particular point. So we're not going to use the closed bracket notation. We're always going to use the open bracket notation. So now just to take a look at the second example, so from, let's go ahead and keep going, -6, -7. So from -7 to, this would be -4, -3. So from -7 to -3, I am decreasing. Hopefully you were thinking that. So from -7 to -3, smaller to bigger, I'm decreasing. I'm constant. From this x value of -3, I stay the same, all the way to this y value of 4. So constant from -3 to 4. And then I'm going to be increasing from 4. So notice the graph jumps down here. And I'm going to start increasing from an x value of 4, 5, 6, 7, all the way to 7. So from 4 to 7. And because there were closed circles at the end, I'm not going to put in negative infinity or infinity. I'm going to stop at the value 7 and -7 on each side. So again, just to recap, we definitely always include just open parentheses for our purposes. It's not wrong to put closed parentheses on this section, but we're just always going to use open parentheses when talking about increasing, decreasing, and constant. The next topic we're going to look at is maximums and minimums. And what to remember about maximums and minimums in general is that they are always y values. So first, we take a look at local and relative maxes and mins. So again, they're always y values, but for local maximums or minimums, there can be more than one. So for maximum, we're thinking a peak, and for a minimum, we're thinking a valley. So say we're given this graph here, and we're asked to identify the local maximums and the local minimums. So to find the local maximums, what I'm looking for is any peak in a mountain. That's what I mean by that. So we're looking for a peak in the hill or a peak in the mountain. So here, there is a local maximum as clearly written. And what we want to do is describe its y value. So we're going to try to line it up here. So the local maximum value, the biggest y value in this little local area, is going to be 3. So the local maximum there is 3. Now here's another little peak in the mountain. So it's happening at what looks like a y value of, let's line it up, let's go ahead and say that's 1.75. So 1.75, and another local maximum or another peak is going to happen at what looks like maybe, I don't know, let's just say that it lines up with 4 to make it easier. So 3, 1.75, and 4 are all local maximum values. So we want to make sure that those values are y values. And then local minimums are going to occur at valleys. So here, down here, we have a local minimum as noted, and we want to describe its y value. So we'll say this lines up with what looks like -2. And then down here, we have a local minimum at what lines up with -6, we'll say. So our local minimums and local maximums are listed here. There can be more than one. For maximum, we're thinking peaks, and for minimum, we're thinking valleys. The other type of max and min are called absolute or global maxes and mins. Again, they have to be y values, but the only difference is there can only be one. There can only be one. So here we're still thinking peaks, but it has to be the highest peak. Or an absolute maximum can occur at an endpoint. And then for minimum, we're thinking that lowest valley or it can also happen at an endpoint as well. So here we have another graph, and if we wanted to find its absolute maximum, so we're going to check basically all of the peaks. So here's a peak and here's a peak in the graph, and we're going to see which one's bigger. But we'd also have to check endpoints. Well, endpoints are way down here, so those two endpoints are not going to be maximums because there are points that are higher than it. But this right here is going to be the highest endpoint that I see. So notice that it doesn't correspond to a particular y value here. So we'll go ahead and make up some numbers. So 1, 2, 3, 4. We'll say that this is 5. So the absolute maximum is going to occur at a y value of 5. And notice here they put absolute and relative. So a point can be classified as both an absolute and relative maximum. That's perfectly fine. And then we'll also attempt to find its absolute minimum. So we have to check every single valley, and here I only see one, so that's a relative min. But we have to see, is there any lowest endpoint? So is there any smallest y value? Well, here's an endpoint, and here's an endpoint. So which one's smaller? So if we try to measure it down, this absolute minimum here, well, this value would be, let's say, -5, and this value here lines up with, let's say, -1. -5 is smaller than -1, and this point might have been -3. So of the endpoints and that relative min, which one's the smallest? -5. So the absolute minimum on this problem corresponds to an endpoint, and it happens at -5. Some other properties that a function can have is they can be described as odd, even, or neither. So odd functions can be rotated 180 degrees about the origin, so the origin being the point 0, 0, and they'll look exactly the same. So imagine just sort of picking it up and spinning it 180 degrees, and then setting it right back down, and it would land right back on top of itself. And the formal way to define an odd function means that when you stick in a negative value for x, that negative comes out in front of the entire function. So here's an example of an odd function. So if we were to pick this function up and spin it around and then put it down, it would land right back on top of itself. And that's what makes this considered to be an odd function. So we could pick it up and spin it, and it would land right back on top of itself. But only if we spin it 180 degrees. Keep in mind, if you spin anything 360 degrees, it will always land right back on top of itself because you've created a complete circle. So we're talking rotated a half circle, and it lands on top of itself. A function is considered even if we can reflect it over the y-axis, so this vertical axis, and it will land right on top of itself. So in other words, here I have this piece of the function, and if I think about this being a mirror, so this y-axis being a mirror, if I flip it, it will land right back on top of itself. So that is considered to be an even function. And formally what would happen is if you were to plug in some negative x value, the negative would just sort of disappear. So with odd functions, the negative gets pulled to the front. With even functions, the negative would just disappear entirely. And then we're considered an even function. And then if something's not even or odd, then it's considered neither. So we can't fold this thing over, right? So if we took half this graph and we try to fold it over the y-axis, it would look like this. So it doesn't land right back on top of itself, that's for sure. And if we try to rotate this thing 180 degrees, the points wouldn't line up. So they're kind of trying to show you that here by picking some random point. So this point is kind of about, let's say, 2, 4. And if we were to rotate it once, first it would end up down here in quadrant 4, and then if we rotate it again, it would end up down here, and it's missing, right? That's not exactly where it's landing. So it's not exactly the same function if I rotated 180 degrees. So to convince yourself, you could just pick a couple of points and think about moving them to the different quadrants, so rotating it twice. So you could either rotate it left, and first you could have said it went over here, and then it went down here, or first it went here and then here, but either way, it doesn't land on top of the same graph, so it's neither odd nor even. And along the same lines, we're going to talk about symmetry with respect to different things. So symmetry with respect to the origin, to the x-axis, and to the y-axis. So symmetry with respect to the origin means that we can rotate the function 180 degrees and it will land right back on top of itself. So symmetry with respect to the origin pretty much means that it's an odd function. And we're going to skip the middle one for a second. Symmetry with respect to the y-axis means we can reflect it over the y-axis and it would be the same function. So y-axis symmetry is a description or a property of functions is really the same as saying that this is an even function. But it's important to know that x-axis symmetry, reflection over the x-axis, does not mean neither. Right? Neither means not even or odd. X-axis symmetry means that I can reflect the graph over the x-axis this time and it will land right back on top of itself. So this top portion of the graph, if I flip it over, this x-axis acting like a mirror, it will land right back on top of itself. So here, this is actually not a function because it does not pass the vertical line test. But we can still have symmetry with respect to the x-axis given special implicitly defined functions that we're going to talk about later. And the last thing I want to talk about in this portion is inverses. So it's not really a property of a function necessarily, but sometimes a function has an inverse, which means that you can switch the x and the y values of one function to obtain another function. So graphically what that means is that if you have one function, if you switch their x's and y's, then it's going to reflect over the line y equals x. So in case you didn't know, this line here is the line y equals x. So let's say I had this function here, this blue function, e to the x, and I wanted its inverse. So every single coordinate point, so this is the coordinate point 0, 1, well, if I wanted to create its inverse, I would flip the point. So instead of 0, 1, I would put the point 1, 0. And then this coordinate point here would end up flipping and becoming this coordinate point. So each of them is sort of a mirror image over this line, y equals x. So each of them sort of has this corresponding point across this line. And that's considered a function's inverse. So here is a little bit of an interesting one here. So the blue function's inverse is the red function. So every point has this corresponding point on the other side of the line y equals x. Now the most popular set of inverses are e to the x, which is the blue graph pictured here, and natural log of x, which are two functions that you should get very familiar with. And that takes us to the next portion of the videos. Classifying functions. So in this class, we're going to deal with particular types of functions that come up relatively often, and those types of functions have classifications. So really, functions can be broken down into these 7 categories. Polynomials. So examples of polynomials are listed below. So polynomials are terms that are added or subtracted which have variables raised to positive whole number exponents. So 4 is a positive whole number, 3, this is x to the 1. So we can't have any fractions and we can't have any negative exponents to be considered a polynomial. Exponential functions, that's when the variable, instead of being the base, it is the exponent, the variables and the exponent. We deal with logarithms, so logarithms being the inverses of exponential functions, so the most popular one being natural log of x. Trigonometric functions, functions like sine, cosine, tangent, and modifications of those functions. Inverse trigonometric functions, so the inverse of trig functions. So those have special notation such as arctan of x or sine inverse of x. So these are interchangeable notations. This to the little -1 symbol, or arc is the inverse notation. We deal with rational functions. Rational functions are polynomials over polynomials. So here I have x to the positive 1, x to the positive 1. Each of these are polynomials, so polynomials being divided by each other. And then finally, we deal with root functions like the square root functions, or this is a third root function or cube root function. So these are the types of functions that we deal with, these 7 categories for the most part, and combinations of these 7 categories. Now, this is going to actually be a very short video for me, but this might take you a little bit more time outside of the video, because the next thing I'm going to show you is what I consider to be the 14 basic functions. So I turned it into a PDF document that I expect you to print out and memorize. So these 14 basic functions fall into these categories, and it is very, very important that you know what the graph of each one looks like and the properties. So switching over, here is this PDF printout of the 14 basic functions. So this first function, f of x equals x. The domain of this function, x is in, this little weird looking e symbol means in, so the domain is all x values that are between negative infinity and infinity, or all real numbers. The range, or the y values, are also from negative infinity to infinity. This thing has no horizontal asymptotes, no vertical asymptotes. It is an odd function. Its x-intercept is 0, 0, y-intercept is 0, 0, increasing from negative infinity to infinity. It's increasing everywhere, and so it's decreasing nowhere. So for every single basic function on here, I have gone ahead and written out all of its properties that you should know. So you should not only know every single graph and recognize it by its function, but you should also know all of its properties prior to day one of the class. So I suggest that you print this out, maybe print it on a thicker cardstock and turn them into, note cards of some kind. This is definitely something that you need to know. So this is the absolute value function. So this one doesn't fall into any of the categories, but it's a really important function, the absolute value function. This is a polynomial, x squared. The square root of x, there's our root function. Here we have x cubed, another polynomial, and the cube root of x. The natural log function and the exponential function. So I said those are two very important inverse functions to each other. This is a rational function. This is 1 over x, or a formal name for it is the reciprocal function. And here are its properties. This is 1 over x squared, another function that comes up relatively often in AP Calculus. And then we have our trig function. So we have our sine function and its properties, our cosine function, the tangent function, tangent inverse, and that is the last one on this list. So there are, of course, many other functions that we're going to deal with in calc, but a lot of them stem from what I would consider these 14 basic functions. So they are functions that you will need to absolutely commit to memory. Alright, so hopefully you went ahead and memorized all of those 14 basic functions, because now we're going to translate and reflect each of them. So let's say we're given some original function f of x. Translations to the graph means that we shift it either left or right, it's a horizontal translation, or up or down, that's a vertical translation. So we shift horizontally, left or right, when we're affecting the x value, which should make sense because the x value is on the horizontal axis. So if we ever add to the x value, then we're going to shift the graph to the left c units. And if we ever subtract a number from the x value, then we're going to shift the whole original function to the right c units. If we add to the outside of the entire function, that's going to affect the graph vertically. So if we ever add to the outside of the entire function, we're going to shift up. And if we ever subtract from the entire function, we're going to shift the whole thing down. And then we can also reflect the graph, and that happens when we multiply by a negative. So if we multiply the entire function by a negative, that's going to be a reflection over the x-axis. And if we only multiply the x by a -1, then that's going to reflect the function over the y-axis. So all of these are properties that you're going to need to remember so you can translate and reflect the 14 basic functions that you've memorized. So let's do some quick examples, all on the same xy plane here. So let's go ahead and draw ourselves a little xy plane. And we're going to start by graphing x squared minus 4. So first thing we need to remember is the parent function's graph. So the parent function is, what original function, what basic function do you recognize here? So the basic function to be recognized in x squared minus 4 is x squared. So what you would need to do is draw yourself a sketch, and I'm going to draw it as a dotted function. I'm going to draw myself a little sketch of x squared. So I know that it goes through 0, 0 and looks like this upward facing parabola. So here is x squared. Well, what I was told to draw is x squared minus 4 to graph. So I have to decide what kind of translation is this. Well, x squared is the original function, and I'm subtracting 4 from the entire function. So I fall into this category of a vertical translation, where here's the original function and I'm subtracting a number from it. So this is going to move my whole original function down 4 units. So I was at 0, 0, 1, 2, 3, 4. Now this whole thing has to move down to -4. And it's going to retain its shape of an upward facing parabola. So now I've gone ahead and graphed as the blue function x squared minus 4. So now the second thing we're told to graph is x plus 4 as a quantity squared. So it still has a parent function of x squared. So that's still the graph that we're working with, this black dotted graph of x squared. But now you'll notice that we're adding to the x value. So we're adding 4 to x, meaning it's a horizontal translation to the left c units. So if I'm adding 4, this original point is going to have to move 1, 2, 3, 4 units to the left. So now this black dotted graph is going to turn into an upward facing parabola still, but shifted to the left 4 units. So this red graph is now the graph of x plus 4 as a quantity squared, because I was affecting just the x value inside the parentheses, and this minus 4 was on the outside of the entire function in the first part of the problem. And then finally, let's take a look at a reflection. So here I have a -1 being multiplied to the entire function, so negative x squared. So this negative's on the outside. This thing is going to reflect over the x-axis. So the horizontal line is the x-axis. So what happens to this black dotted function is that it flips over and becomes a downward facing parabola. So again, I can imagine this x-axis. A reflection is like a mirror image. So I reflect it over this mirror that is the x-axis, and now it's a downward facing parabola. So this green graph is the graph of negative x squared. So we learned I can translate and I can reflect a graph, but I can also stretch and shrink a graph that I'm originally given, one of those basic functions. So I can have vertical stretches and shrinks or horizontal stretches and shrinks. So let's look real quick at horizontal. So notice that here I have this c value that's being multiplied to x. So again, anytime something's happening to the x value, so the c is just right next to the x, it's going to be a horizontal action that's happening. So when I affected the x earlier, it was a movement to the right or to the left horizontally. If I multiply c by x, this is going to be a horizontal stretch or shrink. So the stretch or shrink part depends on the type of number that c is. So if c is a number between 0 and 1, so in other words, if it's some fraction like a half or 1/4 between 0 and 1, then it's a horizontal stretch by 1 over c. So whatever that fraction is, it's going to go on the bottom here and become 1 over c. And if c is bigger than 1, then we have a horizontal shrink by 1 over c. And then the more common one that we're going to see, though, is a vertical stretch. And that happens when the c is being multiplied to the entire function. So not just inside with the x, but if the c is being multiplied on the outside. So if that c is between 0 and 1, then we're going to have a vertical shrink. But if the c is greater than 1, we're going to have a vertical stretch. So these are rules that I think are kind of easy to get mixed up. So it's really important that you try to not only memorize them, but really think about what's happening, what we mean by stretch and shrink. So we'll look at a couple examples below to try to help keep it straight. So here's our xy plane. You'll notice that we are again modifying x squared, the x squared function. So this is actually going to be two different things. I'm going to ignore the -4 for a second, just to talk about the stretch that's happening first. So here, x squared is my parent function. Let's jump straight to drawing x squared as my original function going through 0, 0. So now we have this 2 that's being multiplied by x squared on the outside. So the 2 isn't just with the x, it's multiplied to the outside of the function. So what we're going to do is we're going to go to the vertical stretch category because I have this 2 outside, and c is greater than 1. So the number being multiplied to x squared is 2. 2 is greater than 1. I'm falling into this category here. So it's a vertical stretch. What does that mean? So vertical means up and down. So if this is the original function, what I'm doing is it's like I'm taking the ends of this function. So this is sort of the end of the function, and this is the end of the function, and I'm pulling it up. So it's like if the function is like a rubber band, and I'm pulling the ends of it vertically up and down. So what's going to happen is 2x squared is going to be inside x squared. It's going to be more narrow. It's going to fall inside of the original function because I'm pulling it up. I'm stretching it vertically. So this red function is 2x squared. But then I'm throwing something else in here. I have this minus 4. So minus 4 is on the outside of the whole function. So when I subtract, that means I move down 4 units. So now it's going to go 1, 2, 3, 4, down to negative 4. So now what I want to do is draw that same narrowness to the graph, but shifted down 4 units. So now this red graph is 2x squared minus 4. So that there was the graph of 2x squared minus 4, applying the vertical stretch and a vertical translation down 4 units. Let's go ahead and play around with a different function. Let's go ahead and try 1/2 x cubed. So we'll go ahead and draw another xy plane. And we're going to have to start by drawing x cubed. So you can see that that is going to be my original function. So x cubed, I'm going to draw it as a dotted function. Looks like this. It's one of the ones that you should have memorized. So it also goes through 0, 0. So here's my x cubed function. And now we have this 1/2 in front. So 1/2 is between 0 and 1. It's in front of the entire function, right? 1/2 times x cubed, so it's being multiplied in the front. So this is going to be a vertical shrink. So what that means is that, again, I'm sort of taking the ends of my function, I'm thinking about it, and instead of stretching it, so I'm thinking about pulling it this way and that way, that would be a stretch, I'm shrinking it. I'm like mushing it down. So if I do that, if I think about it pushing together, what's going to happen is it's going to end up being like fatter. It's going to end up being a fatter graph. So this is kind of like a skinny little line, and so now it's going to end up just a little bit wider. So this is going to be the graph of 1/2 x cubed, or a sketch of the graph. So notice it's just a little bit, it goes a little bit further out as opposed to this one, notice, went inside the graph. This one sort of goes outside the graph, but still maintains the general shape. And then lastly, we'll go ahead and draw the third and final graph for 2x squared. So let's go ahead and put it right here. It's going to overlap a little bit. So notice x squared, still that parent function that we're starting with, that original function. So here's my x squared. We're going back to that one. So what's happening here? The 2 is right next to the x. So now we're talking about a horizontal stretch. So when 2 is greater than 1, so I'm in this category here now, I'm going to have a horizontal shrink by 1 over c, where c is 2. So this is a horizontal shrink by 1 over 2. So a horizontal shrink by 1/2. So horizontal meaning left and right, right? Instead of up and down, thinking left and right. So now instead of taking like the top and the bottom of the function, I'm thinking about taking the left side and the right side of the function. And if I shrink this thing, what's going to happen to it? So if I take the two insides and I push them together to shrink this thing is going to end up on the inside of x squared. So a horizontal shrink seems a lot like a vertical stretch. And let's think about that for a second. 2x is a quantity squared. This is like 2 squared times x squared. So this power of 2 does distribute because this is multiplication, not addition. So this is like the same as 4x squared. So 4 is now in front of the entire function. It's like a vertical stretch by 4. So a horizontal shrink by 1/2 is just like a vertical stretch by 4. So that's why this thing is ending up on the inside of the graph of x squared. So we don't end up doing too much stretching and shrinking in this class, but it is important that you understand whether or not the function is going to be inside or outside the original function. The last topic we're going to take a look at is piecewise functions, and this comes up right away when we start to talk about limits and continuity in calculus. So it's really important to know how to graph a piecewise function. It's going to make your life a lot easier when it comes to understanding limits and continuity. So piecewise, the key word here is we break this thing down into pieces. So instead of one whole function, we're going to take a look at it piece at a time. And what we do is we break it down by its different parts of the domain. So this first function here, x squared, when x is less than or equal to 1. So that's the first part of the function. It's saying graph x squared for me, but only when x values are less than or equal to 1. So x values, those are on the x-axis. Here's x equals 1. So I only want the graph of x squared when x is less than 1. So values less than 1 are this direction. So let's go ahead and sketch x squared, which we've done how many times now? So I'm going to go ahead and sketch x squared as a dotted function. And I kind of missed a little bit. And then what I'm going to do is I'm only going to shade in the part of the graph that I'm told to, which is defined by that portion of the domain. So I only want x squared when x is less than or equal to 1. Well, here's 1 right here. And I'm going to go up to the function. Because it's less than or equal to 1, I'm going to go to the function and draw a filled in circle. Whoops. Filled in circle. And then I'm going to shade the portion of the graph that's to the left of 1. So I've defined x squared when x is less than 1. So now I want to define the function negative x plus 1 when x is greater than 1. So for values to the right of 1, I want to be this line, negative x plus 1. So let's sketch the whole line. Negative x plus 1 has a y-intercept of 1, and it has a slope of negative 1. So here's another point on the line. So I'm going to draw this line as a dotted line. So graphing lines should be second nature to you at this point. You should be really, really good at graphing lines. So here's the graph of my line, negative x plus 1. And now I'm told to only define it when x is greater than 1. So at 1, so I'm thinking along this vertical line here at 1, that's where the switch is going to happen between the two pieces of the function. So it happens to cross at the x-axis, but instead of putting a filled in circle, I have to put an open circle because it's only when x is greater than 1. And then I'm going to go ahead and shade down to the right. So this darkened blue part, all the way up to the filled in circle, and then it jumps down to this open circle, and then this green darkened part, that's the graph of f of x here, defined by two different pieces. Now, if you're tempted to put a filled in circle here, this would no longer pass the vertical line test because there'd be a filled in circle and a filled in circle, and we'd hit more than one place. So it would no longer be a function. So vertical line test, hopefully you covered that in your previous class. If not, something you definitely need to look up. But then this would no longer be a function. So that's another really great way of determining which direction to go with the function. The next piecewise function we're going to look at is e to the x and natural log of x. And e to the x is only going to be defined when x is less than or equal to 0. And ln x is going to be defined when x is greater than 0. So let's go ahead and start by graphing e to the x. We should know from our basic functions, e to the x goes through 0, 1, and it has this increasing curve to it. Has a horizontal asymptote at 0, so this thing should not be crossing the x-axis. So I want e to the x when x is less than or equal to 0. So x equals 0 is here. So I'm going to have this filled in circle, and I'm going to shade to the left of it. And actually, I'm going to go ahead and erase the part that I don't need. And then natural log of x when x is greater than 0. So let's sketch natural log of x, which we should know goes through 1, 0, and has a vertical asymptote at 0, and this general increasing shape. And I only want this thing when x is greater than 0. So notice that this natural log function, it does not cross the y-axis here because that's a vertical asymptote. So I'm actually just going to draw the entire graph of natural log of x. So natural log of x is defined only when x is greater than 0, that's its domain. So this whole green graph of ln x is part of the piecewise function, but I'm also including e to the x when x is less than or equal to 0. So here is my graph of this piecewise function. And our last example, we have the cube root of x when x is less than or equal to 1, and absolute value of x when x is greater than 1. So notice I'm trying to review those 14 basic functions. The cube root function, we should know, goes through 0, 0, 1, 1, negative 1, and it sort of has this flattened shape, this flattened S shape. So this here is the graph of cube root of x. And cube root of x is only defined when x is less than or equal to 1. So here's 1, less than or equal. I'm going to put that filled in circle. And I'm going to go ahead and shade to the left where x values are less than 1. And then the absolute value function, absolute value of x, looks like the v. So it looks like this v, and it goes through 1, 1. So I want to shade the absolute value of x when x is greater than 1. So here's 1, greater than 1 means this direction. So if I go up to 1, I would put a open circle. But it's already been filled in by the cube root of x portion, so it stays filled in. You're not going to turn it into an open circle or do something like put an open circle around it. It's already been defined for us by the cube root function at 1. So now what I'm going to do is just fill in the rest of the absolute value function to the right of 1. So this darkened blue portion up to 1, and then this darkened green portion is the rest of the piecewise function shown here off to the left. So that's the last example that we're going to cover here. Some of the topics that I didn't include but that are important to understand are about functions, are how to find horizontal and vertical asymptotes. That is a huge portion to this class that we will be using very, very quickly early on in the class to do with limits. So that is a topic that if you need to know or review, that I definitely suggest that you go ahead and do, is search vertical and horizontal asymptotes. Definitely know the 14 basic functions, their graphs, all their properties long before you come to class. That is absolutely some of the questions that are going to be on the first test that you take in the first full week of the school year. I know that this video moved fast, so if there's any other content or topics that you need to review and you want specific videos, references, then please email me and I will send you those topics so that you are fully prepared for the class.